Our last activity of the year is going to be to find the speed of sound using an air column. It's going to look something like this, something like you see up on the board, something like the apparatus that I have in my hand here. There is a column full of water, and inside that column full of water is an air column. It's really just a pipe. It's open at both ends. But what that allows us to do is change the length of the air column by varying the level of the water, therefore finding different resonant frequencies. So here's what you're going to do first. Okay, you're going to fill this inner tube up, and therefore by default the outer tube with water. You're going to use an Erlenmeyer flask that looks something like this. Now, when you're filling that up, make sure, please, that you keep the inner tube just off of the bottom. Make sure it's not touching the bottom of the rubber stopper at the bottom here. Again, make sure this inner tube right here isn't touching the bottom. If it is, and you go to put water inside the inner tube right here, what's going to happen is that the inner tube is going to fill up with water, and no water will leak out into the outer tube right here. Okay, we want them both to be full to the same level. So lift it up a little bit, pour water into the inner tube. That should allow water to go out the bottom and then fill out the inner and the outer tube to the same level. Okay, lift it up just a little bit, 3 or 4 centimeters, and then fill it up almost to the top. So fill the water level up kind of like this. Okay, 3 or 4 centimeters from the top. Make sense? When you're ready to actually start the meat of the experiment, you're going to take a tuning fork. You guys have all used tuning forks, right? In grade 4, grade 5 science, when you did sound. Okay, you guys know what a tuning fork is, right? You got a tuning fork right here that is going to be somewhere probably in the range of 400 or 500 hertz. Okay, you're going to get a set of them with all kinds of different frequencies. In the end, you can choose whatever you want. But if you use a frequency that's somewhere in the range of 200, 300, 400, 500 hertz, then I'll give you an approximate value of data that you should find. So basically, you're going to know where to look for the resonant frequency that you're trying to find. Okay, if you use a different frequency of 1,000 hertz, that's okay. It's just that you're going to have to look a little bit harder for the resonant frequency, that's all. So my suggestion is use a frequency that's somewhere 300, 500 hertz, somewhere in that range. But again, it doesn't have to be in that range. It can be outside of that range, it'll still work. So you're going to hit the tuning fork, and when you hit the tuning fork, you want to hit it against a little rubber hammer that's going to be included with a package of tuning forks, or there will be for each of them a little triangular rubber block. You can hit it against that as well. Please don't hit the tuning fork against the desk, because you're going to bend it and change the frequency of the tuning fork, and we don't want that. So hit the tuning fork against a piece of rubber, hold it right above this air column. You're going to hear the tuning fork. In fact, if it's quiet in the room, everybody in the room will hear the tuning fork. But it's not going to be that loud. If people are talking in the back, you'd never hear the tuning fork. Okay, that's how quiet the tuning fork is. Now, when you hold it directly above here, and then you start raising this inner tube up, so this inner tube right here goes up, that lowers the water level. Okay, that makes the air column itself longer. Now, at some point, the length of the air column is going to match the frequency of the tuning fork. When you've matched the frequency of the tuning fork, then resonance is going to occur. In other words, you're going to hear that tuning fork be amplified. Okay, you're not looking for a little bit of amplification. You're looking for a lot. Okay, so listen carefully to what I'm about to say. If you're not sure if you're hearing what you're supposed to be hearing, you're probably not hearing it. Okay, when you hear what you're supposed to be hearing, it's usually pretty obvious that you're hearing what you're supposed to be hearing. Okay, does that make sense? If in doubt, ask me. I can help you with that. Okay, is this what I'm supposed to be hearing? I'll tell you, no, it's not, or yes, it is. When you find the length of that air column by raising this up, right, raising this up as high as you need to go until it resonates, when you find the length of that air column, you're going to record that length. And then ultimately, you're going to take the frequency, the length of the air column, find the speed, and then compare it to a theoretical value for speed. So here's what your data table is going to look like. Room temperature, if you do it in this room, and we have the BioLab book, but if you do it in this room, I'll tell you right now, the temperature of the air is 28 degrees Celsius in this room right now. In the BioLab, I'll check again before we actually perform the experiment, but last period when we did this, it was 24 degrees in the BioLab. One group did it on the stairs outside at the end of the hallway. I'm not sure what it is outside. We'd have to take a thermometer out there. I'm guessing somewhere around 31, 32 degrees outside. Write down the value of the frequency of the first tuning fork that you use, maybe 300 hertz, although don't write that number down right now because you might use a completely different number, right? The first resonance level is the first time you hear the amplification of the tuning fork. So as you're lengthening that air column by pulling up that inner tube, at some point you're going to get a length of the air column where you're going to hear resonance. You're going to hear an amplification. Write that down. Okay, then keep raising it. Keep pulling it up. There should be another frequency at which you hear resonance again. It should be somewhere in the range of 3 times the first one. Somewhere in that range. Okay, don't just automatically say if the first one was 20, then the second one is 60, but you know where to look, right? In that range of 60, 58, 62, somewhere in that range. Do the same thing again, but for a different tuning fork. So this time maybe take 500 hertz. Okay, start at a really short length, maybe 4 or 5 centimeters, and keep lengthening it. Keep raising that inner tube until you get resonance occurring or that amplification occurring again. Write down the number of the length of the air column that it occurs at, and then you're looking for the second one, which actually corresponds not to the second harmonic, but it's the third harmonic. Therefore, it's going to happen at 3 times that length. Why the third harmonic? Why are we not looking for the second harmonic? Anyone? Yeah, it's closed air column where we have one end open and one end closed. And if that's the case, then we don't have a second harmonic. We just have first and third harmonics, right? So you're looking at probably, in this one, somewhere in the range of 20 to 30 centimeters for the first one, and then 3 times that, and then probably, depending upon what frequency you use, around 20 to 30 centimeters again. Don't panic if you get 32 centimeters. Okay, that's okay. Just depends on your frequency, but it's going to be somewhere in that range. You don't want to be looking at 6 centimeters for the first one, or even 12 centimeters for the first one. Okay, you don't want to be looking at 45 centimeters for the first one. It's probably going to be in that range or real close to in that range. Then the second one that you hear, which is the third harmonic, should be about 3 times the value of that. So somewhere in the range of 60 to 90, right? Got it? There's your data times 2. Then you're going to answer a few questions. First one is find the speed of sound using the equation that we learned on Friday, 331 plus 0.6 times the temperature. Now again, the temperature in this room is 28 degrees Celsius. In the biolab, it's 24 degrees Celsius. If you do it somewhere else, then we got to make sure that we get the temperature where you did it. The second question involves filling in another chart, but this is an analysis chart. This time you're going to calculate the speed of sound. We know that for the first harmonic in a closed air column, F is equal to V over 4L. But we derived that on Friday, right? F is equal to V over 4L. You want to rearrange that to get V. V is equal to 4 times L times F. Calculate that speed. Get the value for that speed. Then for the second trial, which would actually be a third harmonic, right? If you go back to that data table, our second trial is the third harmonic. F would be equal to 3V over 4L, which V would therefore end up being equal to 4/3 L times F. Get a speed for that one. Then repeat it. Okay, this would be the first harmonic again. This would be the third harmonic again for the second trial. You're going to get 4 different speeds here for the speed of sound. You already got one. This is your theoretical value. This is what it should theoretically be. Okay, these are your actual values, what you found them experimentally to be. Then you're going to average those. Average those speeds. Trial 1 plus trial 2 plus trial 3 plus trial 4 divided by 4. And then you're going to do a percent difference, which is your actual value that you got in question 3, subtract your theoretical value, which is what you got in question 1, over your theoretical value times 100. If you get a good value for the speed of sound here, that number is going to be less than 10%. If you don't have such a good value, it's going to be more than 10%. This template is on Google Classroom already. When you go to hand this in, you're literally just going to open up the template that I've copied for all of you already, fill in the blanks, including calculations, right? Including as best as you can, showing calculations in Google Classroom on the document. And then just clicking submit, like you always do. just a lot less work this time because you don't actually have to write up any formatting issues. It's just a matter of using the template that I've given you. Got it?